From Rohini College of Engineering and Technology. Today I would like to explain the analogies between the electrical and mechanical oscillating systems. So the analogy between electrical and mechanical oscillating systems. The analogy of mechanical oscillations with electrical and magnetic oscillations are so called electromagnetic oscillations in the LCR circuit. In spring system there exist mechanical oscillations, and in LCR circuits there exist electromagnetic oscillations. In spring mass system there exist two forms of energy. They are potential energy of the compressed or extended spring, kinetic energy of the mass vibrating with respect to the mean position. Similarly, there are two forms of energy involved in LCR circuits, namely magnetic energy of the conductor carrying current, electrical energy of the charged capacitor. Analogies. The kinetic energy in the spring mass system is analogous to the magnetic energy of the inductor carrying current in LCR circuit. The potential energy restored by the spring in the spring mass system is analogous to the electrical energy restored by the capacitor in the LCR circuit. The damping force which slowed down the oscillation in the spring mass system is analogous to the resistance which restricts the flow of current in the LCR circuit. So you can see a spring that is having a mass M that is attached to onion. So the mechanical oscillation in the spring mass system. The two forces act on the system or restoring force and the damping force that acts in the opposite direction. Restoring force is minus ky, damping force is minus bv. Here k is the force constant, y is the displacement, b is the damping constant, and v is the velocity. If F is the force required to accelerate the mass m in order to make the mechanical oscillation, the force is given as mass into acceleration. So F is equal to m into A. Accelerating force is equal to the restoring force plus the damping force. So ma plus ky plus bv is equal to 0, where v is the velocity, a is the acceleration. So that equation can be written as m into d square y by dt square plus b into dy by dt plus k into y is equal to 0. So equation 5 represents the second order differential equation for mechanical oscillations. So you can see the electromagnetic oscillation in LCR circuit. Here Q be the charge restored in the capacitor C, and I be the flow of current. So L into d square Q by dt square is equal in dt square plus dq by dt into r plus q by c is equal to 0. Differential equation for electromagnetic oscillator in the LCR circuit. Now by comparing all the terms in both the equations, m is equal to L, that is mass is equal to the inductance L, and B the damping constant is equal to the resistance, and K the force constant is equal to the reciprocal of the capacitor. Thank you.